talking about the bond type. So everybody can identify ionic and covalent. and we know that one of them involves sharing electrons and one of them involves trading them off entirely. So it goes even deeper than that in physical science, or in chemistry. That's what you learned in physical science. So in ionic bonds, you have one atom that gives up its electrons. If it gives up its electrons, its valence electrons, it becomes what kind of ion? Cation. It becomes a positive ion. So you have one that gives up electrons and becomes a positively charged ion. You have one that accepts extra electrons from somewhere out there in the environment because, like, fluorine is just greedy. It will steal electrons from any place and becomes a negative ion. This is like two magnets, okay? This is just like two magnets. So, good enough. Two magnets that have opposite charges, and I've got these actually pushing the like poles together. If I flip these things, they're attracted to one another. They're attracted to one another, and they're held together by those forces of attraction. Have they become one physical thing? No. They're still two separate things, but they are held together by a really powerful force of attraction because of their opposite charges. And like I said, if I put the like poles together, they actually push one another apart. I actually can't. It would take me some force to overcome pushing them together. I would have to continue to hold them. The minute I let go, they're going to separate. There we go. Okay, in an ionic bond, we have one atom that gives up electrons and one that takes them on. And then they're attracted to one another, but they just kind of stand shoulder to shoulder. They don't overlap physically. So we can show this, our old friends, sodium, there's sodium. Well, we can do chlorine or fluorine, any of the halogens. Let's do fluorine. What the heck? It doesn't get any love. So, there are the Lewis dot diagrams for these. Do you remember doing those? Okay. When sodium gives up that electron, we show the formation of an ion like this. It gives that up. It now gets brackets around it, and it gets its charge written outside. So that's now a sodium ion. So just to be real clear on that, let's do that in a color that works on this background. That's a neutral sodium atom. That's a sodium ion. Here's a neutral fluoride atom. Whoops. Here's a fluoride ion, and if you're doing notes on here, you can just copy and paste. Makes it pretty nice. Okay. And I kind of like the visual. For those of you who are real visual learners, I find that this helps me. The fact that these things are in brackets, you can think about, if we kind of move the charge up and out of the way, you can think about these two things standing shoulder to shoulder, but not overlapping, as if their brackets were touching, but they're not mixing their electrons. They're just side by side. They're like two magnets, attracted by opposite charges, but their physical surfaces have not merged. Okay? So, ionic bonds are formed by the attraction of large numbers of cations and anions. Kind of like my paperclip magnet sculpture that I've got going up here this year. We've got lots and lots and lots of magnets being attracted to lots and lots and lots of paperclips. That's kind of what an ionic compound looks like. You've got all these positive and negative charges going whoomph. It's like a giant, crazy ball of attractive forces. The other kind of bond is covalent. And this is why I ask, has anybody here ever been the captain of a team? What do you call it when they have two captains? They call it co-captains. What do co-captains do? They share the responsibilities of being a captain. And that might be like, making sure that you have scorekeeping. I don't know what captains do. I was never a captain of anything, believe me. But they share the responsibility. In a covalent bond, two atoms share their valence electrons. They actually share their valence electrons. So the easiest way to show this is to use something kind of like the, more like what we call the Bohr model, where we show those energy levels. So let's make clear that this is ionic bonding. And if we go to carbon and oxygen, which share stuff frequently. So carbon and oxygen often bond covalently. So we have carbon, and it's got 4 electrons on its outermost main energy level. It would like to feel like it's got how many? How many does everybody want? 8. I should have done this with ammonium, but too late now. Ha! So we've got oxygen, and I'll do a sort of a Swedish O so that we know it's an O, which has got 1, 2, 3, 4, 5, 6, and we're going to make 2 of those. Copy, paste. This is a terrible example because of double bonds, but oh well, like I said, too late now. So these guys are actually going to overlap their orbitals. And in doing so, they each get to feel as though they have the right number of electrons. And these guys are each actually going to share 2 electrons. So they're sharing 2, they're already sharing 1. Well, they're sharing 2. So 1, 2, 3, 4, 5, 6. Oh wait. One, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. This one has to share 1 more. One, 2, 3, 4, 5, 6, 7. Eight. So they're actually overlapping their orbitals. They are physically merged. This is like if you melt 2 pieces of plastic together and then stick them together. We're not talking now about 2 surfaces that are, separate objects. This is a terrible drawing. I'm sorry. I'm going to do a better example. But these guys are actually sharing their electron cloud. Let's do NH3. This is ammonia. You may have seen it. It's a household chemical. It's pretty common. Nitrogen starts off with 5 valence electrons. Hydrogen starts off with 1. We can show this using Lewis dots like that. There are multiple ways to represent this, is what I'm trying to say. We can show that and show that they're sharing. We can also show the nitrogen has 1, 2, 3, 4, 5. Hydrogen just has 1. And so hydrogen will come on over and share that 1 in exchange for sharing one of nitrogen's. To feel like it's got 2. To feel like it's a noble gas. Oops. Okay. So they're actually physically overlapping. They are sharing electrons. Now mind you, drawing them with the energy levels like this is just a way to help you understand the concept. It's not a way that we're ever going to represent this again. It's just so that, you know, we see the visual understanding that they're sharing. So this is a representation of covalent bonding. Elements that are bonded covalently are co-captains of the valence electron team. And I swear to you, I was teaching chemistry for an entire year before I could keep straight ionic and covalent. I don't know why. So I'm hoping that the way I'm explaining it makes it easier for you. So they're sharing electrons. They're sharing those electrons. Now that means that those electrons can move anywhere within the electron cloud that's now surrounding this compound. Okay. Well, so you're at far... Well, clearly. It's good to have an arch nemesis in life. Keeps one motivated. Very few things are entirely at one end of the continuum. There's always the exception that proves the rule. Most things exist somewhere in the middle of the continuum. So where a bond falls on the continuum depends on how strongly each atom attracts the electrons in that bond. Do you remember the picture we drew about electronegativity? Let's do that again. So I'm going to go back and I'm going to borrow this drawing, copy, and I'm going to paste it here. And this is, of course, ammonium, NH3. Well, if I think about this in terms of the fact that they're sharing an electron cloud, and I can actually kind of redraw this to reflect that reality. So we know that whoops, not a color that works. Nitrogen has an electron cloud, and hydrogen has its own little electron cloud, and we say that they're overlapping. And when they overlap, they actually kind of become one big, happy electron cloud. But the thing is, not everything shares evenly. And so some elements have a much stronger attraction for electrons than others. So after they bond, in this case, nitrogen is able to attract those electrons more strongly. We'll continue this tomorrow.